simple logic. I'll show you a few examples how to manage with digital logic, and after that, when we summarize the knowledge about digital systems, we may open next interesting topic. We may start the next topic with devices which are used in the area of programmable logic devices, FPGAs, PLDs techniques. Last week I showed you that electronic circuits, especially with that small IC. There is a small because the BGA enclosure. So we talk a little bit about that circuits. So I think you know everything about the digital logic. I think you remember the XORs, you remember AND OR gates, remember the multiplexer, and I think you has enough knowledge how to build simple logic, digital logic system. Today, after the short introduction about today's topic is a review of programmable logic devices. I think there's the good lecture for online lecture. I show you some kind of history of programming logic devices, and the part of history will be the connection technology and old programming structures. And next, I show you places when we may use the programmable logic devices. Few examples. One part of my own project, and next I show you few integrated circuits from Altera, Intel, and Xilinx. And at the end of that lecture will be design flow. Maybe I will change the position of that schedule to better understand the idea of programmable logic devices. There are 5 benefits of FPGA technology, PLD technology, programmable logic devices technology, or field programmable gate array technology. The first is performance. Why performance is has a key role in that structure? Because maybe 20 years ago, programmable logic devices was only for professional systems. After some marketing acting, programmable logic devices started to use in domestic application, home application. 20 years ago, FPGA was only in professional application, and was very expensive. Time to market, next benefit. We talk a little bit about that circuits. Talk a little bit about the project of PC board. Let's assume we are the manufacturer of the TV sets, and we have line of TV sets, and in the rush, someone invent new technology of coding. We should change everything on the PC boards, change integrated circuits, but when we use the FPGA or programmable logic devices technology, we change only internal structure of that integrated circuits. We change only the program, this better well the structure, inside structure of the integrated circuit than program. We may change everything inside the integrated circuits using one programmable process. So we are started new TV set series in few weeks, not in few months. Cost of that integrated circuit. If you would like to buy one FPGA from electronic shop, the cost is about the simplest one. The cost is about $10. But in mass production, the cost will be very small. So after Intel acquires Altera, after collaboration FPGA factories with siliconium vendors, the cost is very small. Reliability and long-term maintenance. Let's assume we are producer, we are vendor for integrated circuits. We produce a lot of that circuits, and sometimes the factories stopped the production of an integrated circuit, and we don't we cannot buy that circuit. In FPGA technology, the time life of simple integrated circuits is about 20 years. So if you start to project and a system today with new FPGA integrated circuits, we suspect that 10 or more years in the future we may working on the same technology. There's the picture with timeline, the chart with timeline when the transistor was invented. When the first integrated circuits was designed up using the transistors, static RAM, digital, the dynamic RAM, static RAM with registers, dynamic RAM with capacitor, very small capacitors, set of capacitors in the structure of integrated circuits. Next, based on that the integrated circuit technology was extended to microprocessors, and near the same years was built up the simple programmable logic devices. Simple also means they have few gates, few registers. There was enough for solve problem, which was 20 years or 50 years ago. Also, when mass production of integrated circuits started, also for special application, the vendors produce advanced specific integrated circuits. There was small series of integrated circuits dedicated to only one task. For example, controller for blender, controller for washing machine, and that controller was closed in the integrated circuit, and only one vendor used that integrated circuit, one factory which produced that washing machines, and only one producer of the integrated circuit was. About 80s, the market opened for new technologies, especially for computation technologies, where microprocessor was connected with programmable logic devices. So in that time, started to connect that technology with microprocessors, and programmable logic devices were so small to solve some tasks, to solve some problems, which for which microprocessors, microcontrollers have small power. For example, large data connected with the video systems. So processor in 80s was so with so small power to solve, for example, blending. But FPGAs, which relies only one function, the power was the computation power, of course, was enough. So that market grows in 80s last century, and next goes to today's. FPGAs, PLD, I use that too. Abbreviation in the same sense. Maybe 20 years ago, there was difference between that two technologies. Nowadays, that technologies are mixed, so we may talk about the FPGAs and PLDs at the same time on the same lecture. Okay, the first market segment is ASIC and custom silicon and advanced specific integrated circuit. We project any controller for mentioned washing machine, for example, and we achieve special function in integrated circuit. We would like to have to obtain only one integrated circuit with some inputs, with some outputs, and that outputs direct control motor, for example, direct drive motor, and the inputs directly are connected with the touch sensor, capacitance sensor. Of course, it's possible. There are a few vendors in the world that can produce any integrated circuit for us. So we may start to project and next use that integrated circuit. But there is the closed technology. When we make a mistake, we should repeat the whole process of design. So it's that technology. It's for the native ASIC technology is only for professional using only. After test of integrated circuit, we may make a production. So the cost is very huge. But we may replace idea of that technology with FPGAs. I show you a simple digital system last week, and we may, like that digital system, project the huge integrated circuit with a few desired function. Next market segment is digital signal processing. Digital signal processing, for example, for audio system, for example, for video systems. Everyone use the audio equipment. Every one of us here listen to radio, hear the music, and we may change the properties of that voice in the easy way by signal processing. When we trade signal, the music or voice as a kind of a signal, we may change the properties of that signal. For example, cut off some frequencies, add some frequencies, add echo, cancel the noises. Everything is possible using digital signal processing, and FPGA are also designed to work with signal streaming like voice, like video systems. For example, we extend the voice, extend the music into the screen. So we may, in the same way, change the properties of the of our video signal. For example, when we cut off some frequencies, we introduce the filtering of the noise. We may blend the background on the based on the behavior of the signal changing. Also, we may mix it to signals. So using DSP technology, we also may introduce non-linear behavior of the signal. So it's easy using the FPGA, and that structure may be changed during the design the system. It's easy to connect in another way our gates, our registers. Embedded, next market segment, embedded microcontroller applications. Let's assume we would like to design a controller for children toy. For example, trumpet, for example, the bear which is dancing. So we may use small as possible integrated circuit with few inputs, with few outputs. And the part of that system is the microcontroller, which achieve the stack operation, the operation which coming one after one, and small part FPGA realize the connection with for example, the motor for the dancing beer for drinking dancing bear, and manage any sensor. Another segment market or also embedded microcontroller application. There are no simple toys. There are also very complex system like a smartphone. When the part of the smartphone is working as a communication system, part is working as a management of the voice and a management of the video. We change the firmware inside our smartphone, but we don't know what we change. Partially, we change the program to operating system to manage the whole our cell phone, but partially we change the DSP, digital signal processor, which goal is to control the voice, to cancel the noise, for example, and inside that cell phone, the sound function is realized using the FPGA because it's easy, because we project the one PC board for few cell phones. Okay, next market segment, which grows last years, it's a physical layer communication chips. In normal network, Ethernet network, the speed is 1 gigabits per second, but for professional application, we might find 10 gigahertz on the concentrator, or 100 gigahertz, 160 gigahertz, because I think the 160 is the some border in siliconium, because frequency is very high, and only pure digital like gates can manage with that frequency. But our FPGAs there are sets of that simple gates, but someone connect that technology with management of the physical layer during communication. So based on FPGA, we may test few technologies to control, to send and receive the information, the data using high-speed networks. And last year, we are very often using the FPGAs for reconfigurable computing. Let's assume we have a very complex spreadsheet, for example, Excel, and every function is the same. For example, set of few multiplication and some additive cells and some other operation, and we may block. We may put in the block that operation as a one function. It's possible when we connect microprocessor and FPGA, it's possible to realize that function, that specific function, on that gate register structure, and the result will be faster than the result computed by the microcontroller. So, for example, Intel and AMD, Intel connect Xeon processor, professional line of processor with Agile technology from Altera. And for example, in our spreadsheet, when we have that complex function, our complex function, only one is realized on the configurable structure as a FPGA, and a lot of data are put in that structure, and the result is faster than it would be computed by the microcontroller. So a few years ago, FPGA started very rush. Started his new market is the markets segment. Okay. We talked about the digital system. We talked about the market segments where we may use that technology. But what that technology is? There is a very interesting picture. Let's assume we have a lot of gates, registers, another gates, but and also we have a set of inputs and set of outputs. Their gates and register are not connected together, but we know that we have set of gates, set of registers, set of an arithmetic elements inside the structure. After the programming, for example, there is the program. After the programming, like that, we obtain a structure, but that structure consists gates. Gate here, it was, for example, that gate, the input register, some output register, some arithmetic blocks, and after that hypothetic mask, we may program. The program is not good word in the sense of FPGA, it's CPLD, because as a program, we in the program sense we see the structure with one line, second line, third line, and after one operation, another operation is doing, and after that operation is finishing, another is doing. But in a field programmable gate array, we make a programmable structure. We put some mask which represent the digital structure. For example, there is the digital structure here. That digital structure has two inputs, and we may program, put a mask for example, one we put here and put here, and the output we have the function y, it's A, not B. Yeah. So using that mask, which can be represented by that field, we may obtain, we may program, we may make a new digital function, and that's very simple digital function, but in practice that functions should be more complex, as I mentioned the spreadsheet function. Yeah. Okay, I made the simple program. Okay, and some part of history, programmable logic devices. Wait a moment. Okay, we are allowed.
We hear you. Yes.
Okay. Okay, and I'll check the the amount of the group. So I back to the our lecture. Connection technology, some part of the history of the programmable logic devices. The FICE technology was the fuse technology. I show you the example for that technology. That system with fuse was one-time programmable, non-volatile, and technology was very old technology as a bipolar transistor. Next technology, which helped us to solve some digital system problems, was the EEPROM. EEPROM means electrically programmable random only memory. I show you example how to use memory to solve some digital structure, the problem with the structure. And system was reprogrammable, yes, because we may program using special programmer and clean the structure using ultraviolet lamp. The structure is not volatile, and technology was the CMOS. It means the complementary metal on silicon transistor. UV means ultraviolet. Sorry. The next structure was the reprogrammable structure EEPROM. First E means electrically reversible programmable random only memory. That integrated circuit has a possibility to program in circuit and maybe clean and reprogram also in circuit. The structure was not non-volatile. So non-volatile means that after we switch off the power supply, and next we switch on the power supply, the information is achieved inside the structure. And technology name is electrically reversible complementary metal on silicon. And next structure is static RAM. Static RAM should be maybe here between the fuse and EEPROM. Okay, static RAM we may program inside our PC board, inside the circuit, but after we switch off the power supply, that memory is clean. So we should, after next switch on our system, we should reprogram that structure. Next technology is technology which described that siliconium technology, which described that connection technology is complementary MOS. And last was anti-fuse, like some kind of opposite of the fuse. Fuse was made on the bipolar transistor. Anti-fuse is based on the complementary MOS transistor. There are the difference. But last day, the anti-fuse technology is started to grow, probably because it's some quantum relation, quantum physics relation can be represented by behavior of the anti-fuse CMOS plus technology. But there is my suspicion, but I don't know. Okay, I show you the idea of programming fusible links. For example, we have a structure like on that picture. Here we are connected in a pure system here, here, and here, and that elements are called fuses. And the programming process is based on destroy that fuses electrically. Nowadays, electrically, 30 years ago by lasers. So when I destroy, for example, that connection and that connection, I introduce some kind of mask, some kind of programming, so our result should be like that. When I change something different, for example, when I leave a structure like that and that, here is the and y is a negative a here. So when I connect together to that structures, I obtain, for example, y. It's a. There should be a b, or y should be a plus b, because there's the same as a b. I think you are good in that type of logical conversion. So the old structure as fuse, I as mentioned, was the platinum fuse, and we may destroy the connection between two nodes. And nowadays we use a very small and very teeny siliconium connection, or sometimes aluminum connection, and during high current we burn that fuse, so we destroy the fuse and make a gap. So there is the old technique and new technique. Antifusible, it's that technique which I mentioned on the previous screen. There is the structure before programming is this. There are connection here. After we have some kind of gap. Of course, when we would like to program that anti-fuse and fuse structure, we put a mask, and based on that mask we change the physical structure of that integrated circuit. We should design that mask, we should design the properties of that mask, and for the properties of mask we should design the circuit. and we should test that. That's it. Okay, in the ROM cell, random only memory, and also in RAM only random access memory, there's the same idea. We have some memory with address and data output line. For example, address is A0, A1, A2, A4, and data is D0, D1, D2, D3. 4 bits address position and 4 bit at the output, or at the we may program the cells of the memory, because the address here is of that cell is 0, 0, 0, 0, and D is equal 1, 0, 1, 0. Next address, for example, it's 1, 0, 0, 1, and the data value is 1, 1, 1, 1. Okay, if you remember the tables, A3, A0, etc., and D0, etc., so we may use that, sorry, 1, 0, 1, 1, 1, 0, 1, 0, for example. Yeah, we may program which data output is on that address. So that addresses are inputs and data are outputs. So we may realize any function. For example, for function like that, let's change to 0 here. We have NEXOR. So we have the NEXOR function. When we program 1, 0, 0, 0, 0, 1 inside the ROM cells, we may build up the NEXOR function. When we change the data inside that memory for other value, for example, D1 will be 0, 1, 1, 1. So D1 looks like A3, A0 plus. Yeah. So in that way, we may build digital system, and response is very fast because we have some information inside the structure, and we may use that structure as a RAS output. So it's very easy to realize any function, but memories. Okay, the kind of memory is EEPROM. EEPROM is a memory which can be programmed, and they keep the values. There are the technical details which is inside the source, drain, and control gate and gate. Transistor is the most metal silicon transistor. When we introduce some floating gate here, we may program that floating gate, so we may we are open for the information for the activation of that transistor, or close the activation of that transistor. So during activation, the transistor should be 0 or 1, or always one, as I remember one. The one is natural output of the EEPROM. So we may control the seals of the memory. We may program at once, and next we may use technology like here. When we would like to change the program, change the mask, we should destroy all mask by ultraviolet light. Very often EEPROM, which are designed for a few times using, has an eye with structure inside. There is the pure EEPROM structure inside. The EEPROM in that structure is here, and the rest of that siliconium is, for example, microprocessor in that example. Here we observe the structure via the open glass via the eye. After cleaning the EEPROM, we should glue the eye to avoid some rise. Another type of memory is the electrically irreversible programmable random only memory. Internal structure from our point of view is the same. By the floating gate, which blocked the influence of the normal gate, of the control gate, can be removed by electrical, can be removed electrically. So that structure is without the eye, and we may program and clear that EEPROM inside our system. But in that system, we should remove the EEPROM from the PC board and put into the programmer, and next goes back to our system. With EEPROM type of memory, its programming is possible when the memory is soldered into the system. Idea, static RAM, random access memory, idea is the same like here, but we should program data. Data should be programmed each time before we started to work. Okay. You record that my lecture, so I leave some notes for you, especially when the notes are important. Okay, PLD. So we know how to realize simple digital circuits, even that circuits are complex. For complex system, it's RAM, ROM memory solution. It's very good solution. But we would like to do something in natural way, like when we design using the blackboard, using the sheet of paper. So and also in the 80s, maybe 70s, last century, of course, the designers didn't need huge structure like EEPROM, like PROM, EEPROM, like SRAM. There are a lot of inputs, a lot of outputs. They want to something small, but also if integrated circuit is smaller, then it's faster. What that was also important. How to deal a integrated circuit which will be faster than, for example, microcontroller, microprocessor. Of course, if the microprocessor is using the memories, the whole time consumes communication with memories. There is the one disadvantage of small microcontroller microprocessors. The designers know that, so memories was too slow to solve some problems, some digital problems. They want to go in another way, in another path, to solve that digital technology problem. They try to do something new. The new structure, simple structures, was a programmable logic array. Programmable array logic, why there are two names? Because two vendors invent something, and programmable logic array, it's a natural name of array with programmable logic elements, but another vendors should change the name, because PLA was a trademark of one of the vendors. Next, they extend programmable array logic to generic array logic. I show you the examples. And next, nowadays we use, even in small application, we use complex programmable logic devices. And of course, completely different technology than CPLD, than pure PLD, PLA, PLA, PIL, was the programmable gate array. We know that in PLA, GLA, the number of gates was about 20. In CPLD, the number of gates was a few thousand. But in FPGA, we assume that we need a few miles, for example, hundreds, thousands of gates. Okay, there is in Polish, sorry, because there is from Polish book. That ABC are inputs, Y is output. Here is ABC, and that scheme means that we have three inputs with its hardwired connection. It's are still connected to input of that gate. So we obtain Y capital is A, B, C. Yeah. When we meet something like that, there is a connection. There is the node. There is the point, which can be programmable. It means we may make a connection during put the dot, or leave alone, so there are no connection here. When we leave alone, there are no connection between, for example, A and Y. So in that construction, in that we have Y it's equal A. In that Y it's equal something else which is connected. Yeah. Okay, the first is the random only memory or memory. We have 3 input and 3 output. First time that structure was used by Bosch Corporation, American part of the Bosch Corporation. and the project was funded by the US Air Force. So the Bosch engineers should solve any problem of digital logic. So they propose memory as a solver of digital system. We have two inputs. As I mentioned, there should be A1, A2, A3. That part is a kind of decoder address. That line is active when we have 3 zeros, for example. That line is active when we have 0, 0, and 1. There is A1, A3, A2. Yeah. So during we put something here on that input, A input on the address input, we choose the line. When we choose the line, we may program response. Q0 will be 1 when I1, A2, A3 should be zeros. When the another position 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. Okay, the rest of position Q O1 is equal to 0. So O1 is equal to A1, A2, A3, and the function, if n is 1, it's 0. So it's plus, plus, and negative. We realize that function only by programming that point. We may change something like that, so we may realize another function using the memory. Okay, 3 input, 3 output. We may extend output. 3 inputs means that we have 8 standard position of our digital structure and some kind of outputs. Okay, there is the memory. We may use that memory as a solver for digital. I show the example. The example is here. We may build a complex function from the table. Sorry, someone knocking on my door. Their part of the memory is the data memory part, data memory area. So that data memory area can be represented by a truth table. So that Bosch solution open completely new thinking about digital systems, about solving of digital logic problems, because the engineers mustn't realize function on the gates. They put truth table in the memory and system is working as a customer wants. It was great invention. It was 65 years ago. Next, engineers want to do something different, because the structure of memory was very huge, and the memory field, the silicon field, was cost. The structure of memory in siliconium is, as I mentioned, is huge. The cost of the integrated circuits depends on the size of the area of the structure, and that memories are not cheap. So the engineers want to think something new, which will be smaller. They propose the Texas Instruments with project for IBM, propose address decoder in a smaller form. There is not full address decoder, because you remember in truth table, for example, we have X or dash. It means no care, yeah. A and D it's here. When we introduce no care, but no care is very often in practical digital structure. So they propose reduced address decoder, like here. We talked about how to find the no care signal last week. So I think you are familiar with that techniques. And right part is the same. The structure, the area of the structure was 1 and third. The first structure. So there was also solution with programmable logic array, PLA name. What is interesting? 1970 solution for professional. 1982 solution for domestic use. So there was the big gap between professional technology and domestic human technology. So there is about 10 years. Next structure, another engineers from monolithic memories propose constant structure on the right side, but changing the decoder address. So we connect together for output 1 and that 2 to gate. So the structure, proposed structure, is based on that that gate, and or is summarizing the system. And is some kind of arithmetic representation of and is multiplication, or is similar to add to signal. So based on that assumption, we may choose the inputs and next summarize in logical, not in arithmetic, in logical form, and we may, based on that system, design also any logical digital system. Okay, but that monolithic memories which introduce that idea. In digital system, we are very often use register to remember, for example, state, for remember the data, for remember any information, and monolithic memories and next latest semiconductor extend the PLA structure for 1D D latch, and that D latch has two inputs, Q and negative Q, and also we may choose that output of PLA structure directly or by negative function. Direct is here as a Q. Remember it last value, negative Q, and we may connect that information to the output pin. And also we may introduce also that remember value as our PLA structure. So based on that system, a state machine can be realized. I think you remember one state, another. I think you remember the coffee machine. Yeah, it may be working like that, like that, like that. So, and one output is here, second should be, for example, here, one output as a full state, a full state machine. So that state machine can be realized on simple integrated circuit. The cost is about a half of $1, and that GAL open completely new possibility to build control system, especially digital control system, like our coffee machine. Our coffee machine can be realized on that simple integrated circuits. That is very, very, very interesting. So based on that, based on that idea, register connected with some array of logic is used in programmable logic devices. For example, the micro seal. Oh, there is the micro seal. The structure is very similar to PAL. There is kind of PAL. There is the flip-flop. The flip-flop it's here, and that microcell is realized as a part of complex programmable logic devices. For example, for 64 structures, that structure inside that part of the integrated circuits. For the rest part of it, maybe 1,000 of that microcell, 1,000 of a register, and thousands of that PAL. The PAL form is something like lookup table. We find the address, we receive the data. CPLD, when the market grows, the output of CPLD can be in different standards and different. I'll show you. Okay, there is the output, the average output of FPGA. It is very similar. The output can be in the standard like 3.3 volts, low voltage differential line, low voltage CMOS 1.8, 1.5, especially for the interconnect with controllers on microprocessors is 1.5 logic. Okay, let's back to our structure. That simple structure is duplicated inside the huge structures, and in FPGA we have a lot of that gates, a lot of register, and the number of register is one of properties of the FPGA. And sometimes when we find the FPGA with 15 number and a magic number 15, it means that FPGA has 15,000 of that registers. That registers are connected in logic array blocks and next implemented on the siliconium structure. And there is typical FPGA logic element. This structure was growing very, very huge. The D is flip-flop is still here. Some kind of element to load synchronous and synchronous clear that D flip-flop mentioned lookup table. And because FPGAs are very often used in arithmetic systems, the producers, the vendors provide, carry on and carry out special signals to connect blocks together to do fast arithmetic system. Because nowadays computations are based on the arithmetic behavior of integers, for example. They should carry in and carry out signals, and of course pure digital lookup table is also achieved in that logic element block. A logic element block can be used in normal mode, in arithmetic mode, and a few another structure. We as a programmer decide about the role of the logic array, logic element in the logic array block and logic array block in FPGA structure. So FPGA structure is very huge, very hard and very hard to program, to predict, to obtain the structure directly based on digital behavior. For structure like GAL, it was easy to build that system based on a set of gates, based on lookup table. But for FPGA, where we have a lot of logic array blocks, we need a special tools to manage that structure inside. I will show you that software on the normal lab, and I'll show you some examples. Okay, very often that structure like that is extended on special designed blocks. For example, input-output with the special designed blocks. For example, memories. For example, even microcontroller like ARM, like NIOS, like RISC-V. We may meet in FPGA structures special blocks, and the special blocks is the memory blocks. Like here, very fast memory. The searching frequency is about 1 gigahertz. And of course, that memory blocks can be used in few configuration, for example, as a pure memory, as a dual port memory. For example, dual port memory is like that here. For one side, we connect, for example, microprocessor. For the second side, first, we connect microprocessor second, and two microprocessors use the same memory separately. So that we may put something inside that memory from from first microcontroller and receive the data by the second microcontroller. For example, sometimes we use PCI Express, PCI Express solution like connection between two separated systems. Okay, there is not important. I/O blocks, as I mentioned, the voltage level is important from Intel for another vendors, and also differential line. But in a high-speed digital system, when the frequency is over 100 megahertz or over 50 megahertz even, we should use differential line. In differential line is, for example, in SATA disk. If you want to, if you open the SATA cable, there are two differential line. Okay, input-output blocks. Output can be in few forms. Output may be open drain, output may be full CMOS output, output may be switch with some kind of latch, and a clamp diode on the opposite side, on downside also is used. And in some structure, we may influence on that diode, on that resistor, and based on the software, we may program existing of the diodes, existing of the resistor, or even, especially in high-speed system, we may program set the value or set the existence of capacitance of the output. That is very important for high-speed digital system. Also, I mentioned, I think, about that. And that's like that. There are FPGA here, and on the opposite side we may find the dynamic RAM. The FPGA and microcontrollers and microprocessor are done in different type of technology than dynamic memory. So very often we need two integrated circuit, one for microcontroller FPGA and the second for like here for the dynamic RAM. So we need the special interface for that RAM, and very often the refreshment of the RAM, which is necessary, is done by the special integrated circuit. The special part of FPGA can manage with that DRAM, and FPGA and microprocessor, which is inside that structure, see that memory as a static RAM. So kind of procedures are done in that FPGA to be easier to working with that memory. The DRAM is cheaper than static RAM. Also, I mentioned about the PCI Express for programming the whole structure, FPGA, CPLD, SPLD, from Altera, from Intel, from Cypress Hill, from Aldex, from Xilinx. We use the same interface based on JTAG standard IEEE 1149.1, .1a, .2, etc. That is not important for you. We may put together few devices, that's FPGA, microcontroller, in a chain, in the daisy chain, and control each other using only one interface. On that board has a built-in interface, that's not chip here, and the USB is responsible for communication with PC. Okay, the last. Okay, we have a quarter. The last example, the last set of examples, FPGA applications. I mentioned last week about this application. First group is automotive graphics processing. The automotive market grows very fast. We need new solution for few months. So it's easy to use FPGA to fast changing the properties, for example, of our display in our cars. The main display and the additional display for the map and for car audio system. Also, car networking grows very fast. We have few types of networks in our cars, especially in modern cars. Special network for the voice, for the music system, for the audio system. Sorry. Special for grab the video signals from sensors. Another network for control the motor for driving. Another network for control elements like air conditioner and whisper, for example. Computer and storage, I mentioned about the high performance computing, and also in storage and storage servers. This is important when you connect together. FPGA can fast when FPGA relies on the one function, it's a good solution to build, for example, data finder. How to find the data in storage like set of disks. Industrial networking, motor control example I show you in military system, especially in the radar system. When we need the information about the time, when we should measure the time, the small amount of time, and ticks is nanosecond ticks, only FPGA can manage with that small time. Wireless 5G, there's the mistake here, 5G infrastructure, and also there's LTE, there's the 4G, it means 4G. And the test of the infrastructure are based on the FPGAs, because it was easy to change the program. It was easy to change the codec for transmission and decoder, of course. And the same problem in broadcasting 4K, which when the 4K grows, everyone TV set has FPGA and possibility to fast changing the firmware. Also, broadcasting and consumer technology, TV set-top boxes, homes that are connected together. In a very serious market, medical technology. I also show you the examples with Hertz Runner. high-speed diagnostic imaging, electromedical devices, drawer for parameters of the human body, and etc. Also in test measurements, as I mentioned, the high-speed wireline, 160 gigabyte per second. That multimedia, a home multimedia station like set-top box, one FPGA can manage with memory, that memory can manage high-speed HDMI, for example, keyboard, USB and SSD, and that disk, and small chipset which connect FPGA with CPU and memory, because it's still hard to do a memory controller inside the CPU structure. I don't know why, but in last solution we may put that 3 elements in one structure, one FPGA structure, and we connect the memory, of course, external. Set-top box, there is the kind of solutions which can be done by Ultra or not Ultra, so there is not important. There is a Blu-ray, DVD, player, recorder system. Everything is done on the FPGA like that, but some part of solution program integrate some kind of program I feed by Altera, or not by Altera but by external vendors. But it's possible to build that system for Blu-ray or DVD or recorder system, HDD recorder system on one FPGA. Yeah? If we have one FPGA, it can do everything. The connection of the network, video, TeraSile, the antenna system. Here, everything can be done in one FPGA, because there are only digital systems. Part of analog is only here. There is analog. There is no FPGA, so let's exclude for that FPGA. A few years ago, I have problem with one type of LCD module. So I start to think about how it works. The LCD module is the flat TV set or module. For example, we have HD. I don't remember the resolution. It's about 1 million. There is why I don't remember, because the resolution of the screen is like that, but the resolution of channel which is used for transmitting the information is higher. I don't remember the numbers, but we have about 2 million points. Yeah, at each point is represented by 3 colors, and each colors is represented by 6 or 8 or 10 bits. Let's assume 8 bits. We obtain 48 megabits per second if we would like to transfer that information. So in one screen, on one screen, we have 48 megabits bits of information. It's a very large amount of information, and we change that information during 10 milliseconds. So we should reconfigure. We should change each point of on every 10 millisecond. It's a huge problem to solve by microprocessor. Decoding is easy for microprocessor because the information is not changing very well, very fast. 1 point to 1 point changing is about 50 milliseconds. But for display that information, we assume that each point change in that speed. So only FPGA can manage with that amount of information in that time. And also we may change the internal structure, so we may implement a function like filtering, blending, mentioned blending, like sharpener. It is very easy function of sharpener and blender, and can be realized on the screen. Home networking system. Next example. We have 5 minutes. Okay. And connection between the few type of networks, a few type of interface like SDD, like VLAN, like PCI Express, like USB, can be done by FPGA. Also in smartphone, mobile, internet device, in professional systems, sometimes smartphone is called mobile internet device. It's a special name. In that system, very often the manager of whole structure is relies on FPGA or on CPLD or FPGA and CPLD. For that solution, okay, application processor is the external processor very often. Nowadays there is the ARM. Audio codec, audio digital signal processing, and management, RAM management, memory management is done by FPGA. Radio frequency transceiver is often digital part of the transmission system is also done by FPGA, but simple CPLD is very often used power management. Why? Because CPLD or SPLD is faster, is smaller than FPGA, than processor, and it is faster. And when we switch on our cell phone, the first element which starts to work is CPLD. Okay, portable media player, this same situation, codecs, video codec, audio codec, etc. Game player. Electronics, toys, I mentioned that. Washing machine, I may show you the example on the next lecture. With that washing machine, the motor control was connected together. Most touchscreen display HMI in PLC systems are based on FPGA. Medical application, the Hertz runner, like here, small CPLD inside. That CPLD, what is interesting, can be programmable outside the body of the patient. And also in cryptography, I think you heard about the Israel made Pegasus system. Probably Pegasus system is based on the FPGAs. There is a Pico S5. I don't remember the vendor. And there are a lot of FPGAs, and that FPGAs has only one function to broke a code. For example, file values. If you are familiar with Bitcoins, you know what is it. That S5, SC5, complex 5 with 72 FPGAs can solve 600,000 of file value per second, or can broke 4 billion of VIP keys per second. It's extremely huge, but we don't use VIP in your home network, but still benchmark remains. So that system can grow 4 billion networks per second, old type networks. Embedded processors, I talk a little bit, and very often we use FPGA, CPLD as a bridge between, for example, I2C and SPI. It's very easy to use that circuit. There's simple digital structure. And few years ago, my student realized the PDP-11 computer like that. The shelf is here. There is the system with that computer and external devices. That computer is still used in American atomic power plants because it's certified for atomic war. I think I don't remember. And my students realize a lot of function of that computer in structure like that. The computer is produced in 70s last century. So he realized the most of function operation system was running on a small FPGA. Okay. Thank you very much for today meeting. For next week, next lecture in the next week. I show you the examples. I show you how to program, how to write a simple program, how to program the device, and I think I run one structure or another and show you some examples. Thank you very much for today meeting. See you next time. As you told me yesterday, tomorrow we have holidays. Holiday, not holidays yet. Okay.
Yes.
Thank you very much. Holiday. One holiday. 1 day of holiday. Okay. Thank you very much. See you.
What about your travel to Astana?